So today I'm just going to give you a little introduction about analog modeling and how we can apply this approach to deep water sedimentary system. And when I talk about analog modeling, I talk about flume tank modeling precisely. Okay. So first of all, let's just talk about what is analog modeling. Why do we create such small scale experimental models of our big natural systems? And since when do we do analog modeling? What is the scaling that we use for our experimental flows? I mean, you can already imagine, since we're scaling them down quite a lot in their dimensions, what are the scales that we use to make them coherent with natural systems? Then I will shortly just talk a little bit about what kind of flumes exist and some of the questions that have been answered with different types of flumes. And the gross of this talk is probably going to be on those three examples that I've stated here, which are three series of analog modeling that I have conducted to study deep water systems. So on this picture, you actually see me. I've managed to get into the flume tank this year, finally, after the long lockdown, and do some experiments. You will see some of the results from that just at the end, because these are the experiments of example 3. So we established analog modeling in flume tanks to do uncomplicated models that can recreate the very complex geological scenarios. And we can simulate evolution of sedimentary systems. And for deep water systems, basically, flume tanks have allowed the investigation of turbidity currents of debris flows since the 1930s. Interestingly, before that, of course, no one has ever tried to really model turbidity currents because no one knew that they are very important agencies to transport sediment into the deep sea. Before the Great Banks event in 1929, it was assumed that in the deep sea, except for hemipelagic and pelagic sedimentation, there's not much happening there. Also nowadays, we already have some instrumentation that can measure turbidity currents and debris flows in situ, but they're very hazardous. So a lot of time these instrumentations get destroyed. So measurements with using these instrumentations are still very difficult, which is why we still make use of our flume tanks. And really, flume tanks haven't really changed a lot since the 30s or even the 80s. Here you see a picture of a flume tank from the 80s, that's the ETH Zurich. And most of flume tanks still look like this. If you wonder who this guy just on the right of this is Philip Kuehnen. He was one of the trailblazers for flume tank modeling in the 1930s. You've probably already all seen like this diagram that is depicted here on the left, that shows the velocity profile and the concentration profile of a turbidity current. Maybe you've never wondered how we know what this velocity profile and concentration profile looks like. And how do we know this? We actually know this from analog modeling, because up until the early 2000s, there had been no direct measurements of turbidity currents in any natural system. So all of these models that we have about turbidity currents, how the velocity profile looks like, the concentration profile looks like, that we can divide them into two regions, the lower region, which has a higher concentration, and an upper region with a lower concentration. the fact that we know that a turbidity current has a head and a body and a tail, these are all, this is all knowledge that we gained from analog modeling. On the right side now, you see, these are some direct measurement of turbidity currents in the Monterey Canyon. For those of you who don't know, the Monterey Canyon is on the western side of the United States of America, in Monterey Bay. And basically you just have to now just switch around your view, because this mooring has been moved from the right to the left. So basically the velocity profile is just switched around, but we can see overall the velocity profile that we get from our models in experiments has the same shape as the actual measured velocity profile we get from natural systems. Just a little bit on how do we measure in like the measurement instrumentation in natural systems that we can use to take direct measurements. Nowadays, there is a very big range of these instrumentations, ranging from just single point moorings, for more sophisticated moorings that can catch sediment, but also measure velocities. Some of them are basically similar to, yeah, well, they're attached to the seabed. Some others are basically buoys, where you have your instruments kind of pointed to the seafloor. We can also use unmanned automatic vehicles, so like little submarines, to study turbidity currents and so on. And now there's also a range of systems that people have looked at with this instrumentation, namely the Congo Canyon, Monterey Bay. We also have the Squamish Delta and a couple of other examples. If you're really interested in this kind of things, there's this article from Claire and others, and they're basically talking about the lesson that they've learned from monitoring turbidity currents from natural systems. Okay, so let's go now more into our analog modeling and how do we scale our analog models so that we can actually make robust assumptions over the currents that we're studying. So there are a couple of scaling approaches that we want to get right when we want to make good assumptions from our analog model. And one thing that we want to scale is either if our flow is laminar or if our flow is turbulent. Of course, if we want to study debris flows, we want to plan our analog modeling experiments so that we actually also get a laminar flow at the end. And if we want to study turbidity currents, we want to establish them so that we can have a turbulent flow at the end of our experiment. And these scaling is basically done with the Reynolds number. And you see here's the equation. I don't want to get into it too much, but basically what the equation does, it is taking the ratio of the inertial forces towards the ratio of the viscous forces. If the viscous forces are stronger, you get a laminar flow, which is very slow and has fluid motions. If the inertial forces are stronger, then you get a turbulent flow that creates eddies and vortices and other flow instabilities. If you've now said, okay, I've scaled for turbidity currents, there's still some other things you might want to consider. One of these things is the fruit number, and a lot of you have probably heard about this before. Fruit number is also an important number, for example, in open channel flows. And when I say open channel flows, I mean systems like rivers. You might also see the equation for the fruit numbers. The only difference for the equation for fruit numbers in open channel flow and these for turbidity currents is basically that we are working with a reduced gravity. Why a reduced gravity? Because our turbidity current and the ambient water around it, basically they don't have a big gravity difference. So similar to the Reynolds number, the Fruit number gives you more or less a ratio between the initial forces, and this time it's against the gravitational forces. So the initial forces, you can transport sediment further out, and the gravitational forces are those forces who basically resulting in your sediment to deposit. And depending on how your ratio between the inertial forces and gravitational forces are, you either get subcritical flows. These are usually quite slow and tranquil conditions, and this is when the Fruit number is below 1. Or you get a supercritical flow. These are fast-moving shooting flows, and everything that has a Fruit number above 1 is called a supercritical flow. And we can change between subcritical and supercritical flows with something that's called a hydraulic jump. And this hydraulic jump basically just indicates that we have a change from a high Fruit number above 1 to a low Fruit number below 1. And I think this figure really nice illustrates what happened with a flow that's above 1, so a supercritical flow. It's quite a thin flow. And after the hydraulic jump, this flow extends and becomes a lot thicker and slower. You can also see this down here in the lower figure where you have the downstream velocities plotted. So you see in the supercritical flow, the overall flow is quite fast, whereas in the subcritical flow, you get these turbidity current that again is this two-parted. Overall, we have less fast flows, but there is a lower part that's a little bit faster than the upper part. It's slower. And then again, you could accelerate your flow and go into a supercritical flow. In this case, if you go from a subcritical back to a supercritical flow, there is no jump, no hydraulic jump. You don't have to, because it's just an acceleration of the flow. So the Reynolds number and the Fruit number are usually employed when you work with 2D flume tanks. Well, if you want, and yeah, what it means, a 2D flume tank, I will just get to that in a second. But if you're modeling a bigger system in a 3D flume tank, you might want to use another approach. Because the traditional approach with using Fruit number and the Reynolds number alone allows for you to study the dynamics, but usually the flows are very rapidly depleted. And so it's not really the best option to investigate for depositional processes. You really want a scaling that allows for erosion, bypass, and deposition at the same time. So with these kind of investigations, we use shield scaling. And shield scaling, you basically have to look at two numbers. One is the shield number, and the shield number tells you if your particles are transported in suspension. So this is one of the things you want. You want your particles to be transported in suspension. And you use the Reynolds particle number. It's slightly different than the overall Reynolds number, because basically it tells you about the characteristic of the boundary layer. And the boundary layer is the layer between the bed and the suspension flow. And you ideally want it to be transitional rough, because if it's hydraulically smooth, you do have a little bit of a laminar layer down at your bed, and that's what you want to avoid. You can see on this figure here that some of the old experiments, even without aiming for it, are actually very well within shield scaling, and others are very far out and they have hydraulically smooth conditions. So these experiments are actually not very well to think about how depositional patterns have evolved. Let's get to the type of flumes that we have. So basically a 2D flume, of course, is in reality also 3D, but we call them 2D flumes because the flow in the flume is always confined within the walls. There is no way for the flow to spread laterally, at least not freely. They are confined. So how do they look like? They're usually like an elongated shape. You can either have lock exchange flumes, which basically means you have a sediment box. You fill this up, and when you want to start the current, you release a lock and the current travels by its own excess density. Or you could have a regulated supply through a pump, and then you would know exactly, for example, the discharge you put into your 2D flow. You can either use your flume horizontal, or you can incline them up to sometimes 10 degrees or 15 degrees. And a lot of them have the option of recirculating the flow. So they're just going through the setup and they get sucked in again and, well, recirculated. Sometimes, if you don't have a recirculating tank, you get the problem that when your flow reacts with the end of the flume, it gets reflected. And to avoid that, some of the flumes have an expansion tank, or sometimes a false floor is used. With the use of the false floor, basically the current that would be reflected can reflect underneath your deposits that you create. So what do we use 2D flumes for? Well, most of all to study flow parameters, but also flow regimes and sediment structure stability. I'm pretty sure you've all seen the stability diagrams for ripples and planar lamination. They were established using flume tanks. We can look, for example, onto the impact of slope breaks, or well, people are now using it for more and more sophisticated work. And this is the exemplary picture that I've put here is, for example, filtering the microplastics through corals. So can corals catch microplastic? What would that mean for coral colonies, for example? And just to give you a little bit more of an image of 2D flumes, so wave flumes and flumes that just testing currents, they are also kind of all belonging to the 2D flumes. This is just an example of someone using one of these recirculation 2D flumes to study supercritical flows and their hydraulic jumps and what happens if they are then transformed to a subcritical flow. So 3D flumes are usually a lot bigger, or at least they are not quite as elongated. They are more square in their geometry than the 2D flumes. And they basically are set up like this, so the flows are not confined laterally. And what they do allow is to sometimes change the topography during experiments. It depends on the setup, but some of them do have hexagons underneath the setup that you can either lift or lower, and then you just create like a depot center or something that's similar to a regional uplift. So you can simulate tectonics. What you also can do is you can use preformed topography for your experiments. For example, you can create something looking like a salt diapir and see how your flows react with that. The picture shows you the Eurotank at the University of Utrecht in one of our experimental setups that I will come back to later. But we use 3D flumes, for example, for things like landscape evolution. So how are erosion and depositional processes reacting to different boundary conditions? How do we fill a basin? And what is the architecture of this basin after the fill? And we can also study turbidity current and contour current interaction. There's a special flume called annular flume. Usually they're circular, and usually they can also rotate. And one of the advantages that annular flumes have is they don't have the effect of inflow and outflow conditions. So if you want to study something for a longer time, let's say the erosion of a specific substrate, you would use an annular flume, because you can always kind of rotate the tank and have these experiments run for hours and hours on a go, and you would have no effect of recirculating your flow. And also pumps would not break down, for example, your flocculated sediment, or in a case what people have studied in annular flumes where they've added some organisms to the sediment, they would also not destroy the organisms like mechanically in a way that would never occur in nature. Well, what are they used for mostly? Well, I already said a little bit about this, but it's basically mostly used for erosion experiments. Sometimes also in these erosion experiments, people want to know what the effect of biofilms are. And there has been this very well-known experiment where people have added worms to the annular flume and see what would have happened if they've been transported for several kilometers, because they wanted to know for the Burgess Shale if all the preserved fossils that we can see there would have been fossils that have actually been in situ living there, or if they could have been transported there as well. Now let's go a little bit into our examples. And the first example is a pretty, well, kind of ground basic question for things in submarine fans, because as you might all know, submarine fans are built by a network of channel levee systems, and these channel levee systems then transition into lobe deposits. So these are the main depositional body of submarine fans. What we can observe is that, first of all, we have these really huge system like the Amazon fan that has very, very long and quite wide lobes. And we have smaller system, for example, the Golo fan, and the lobes that are associated with the Golo fan are overall a lot smaller. And this is one of, yeah, we think the main reason for that is that the Amazon fan is overall very unconfined, but the Golo fan is in a very tectonic active setting, so there is more confinement. But even if you look within a singular system, you can see that there is a big spread between the sizes of these lobes. And I wanted to know, so, okay, it cannot be the basin set up. So why would we see these differences in size? And I used one of the 3D flumes for that, and it's the 3D flume at Utrecht University. Imagine like a swimming pool sized flume that is 11 meters long, 6 meters wide, and 1.3 meters deep. What I did, I basically established a pre-topography, a slope that's 11 degrees steep with a variable base and floor. So for my experiments, I changed the angle, and all the sediment was pumped in to this inlet and then had to travel through a preformed channel and levee before it could laterally extend. The sediment I used was 75% of very fine to fine quartz sand, and I added some 25% of fine to coarse grained silt. The main reason for that being that, first of all, we always have a mixture of at least sand and silt in our natural systems, but also what we have learned before is that if you try to use 100% of sand, in the experiments, we are not adhering to our Shields scaling. And actually the shield scaling is also one of the reasons that the slope has to be 11%, because if you make it less steep, then again, you're not adhering to your scaling. So what kind of equipment do we have to measure now our flow? So while the flow is actually transversing through our flume tank, we use UVPs. These are ultrasonic velocity probes. So from the measurements they take, we later on can get the velocities that the flows have traveled. But what we'll also do is that we scan the whole setup before the experiment and afterwards, so that we can see where there had been erosion and where there was deposition. Again, this picture I showed you before, now you know a little bit more about the dimensions. So you can imagine how big this is. And to actually create this topography, there are already several tons of sand inside the setup. So what does it take to actually do one of these experiments? So we have a mixing tank that has the volume of 900 liters, and to get to a concentration for our input flow, we need 400 kilograms of sediment. So that is what's going into our flume. But before we can start our experiments, we have to create the basin topography. So this means set up the preformed channel, but also decide which kind of basin flow angle we want to use. So if you want to use 4 degrees or 2 degrees, we have to do the laser scan. So we have a picture how it was before the flow arrived. The UVPs have to be set up. The basin has to be filled with water. This takes 10 hours. So that's something that's usually done overnight. Then when the basin is actually filled, flow mixture has to be prepared and all the other equipment has to be set up. And only when all of that is done, the experiment can actually be run. And the run of one of these experiments is approximately 2 minutes. Afterwards, before you can see what has really happened in the flume tank, you have to drain the tank again. So basically only the next day, in this case, you see the deposit that has formed. And then again, you would laser scan your deposit and compare it to the laser scan before. Here is one of these experiments captured by a video camera. So you see the head coming in now, and the spread of the margins to the side. So by now, the head has basically transversed all our UVPs, and the UVPs are actually in a height so they don't interfere with the deposits at all. After the draining the tank, you will get a deposit. Most of the time, if you only have an experiment with a single run, will look like this, quite an elongated deposit. And I have conducted basically to study Lobe dimensions, I've conducted 3 theories. And one, I have changed the basin floor angle. In the second series, I've changed sediment volume concentration. In the third series, I changed the discharge. So to make it brief, basically, when the slope angle was changed from 0 degrees to 4 degrees, the deposit that was created after the flow has been passed through would become more elongated. And this is basically due to the deceleration at the break of slope. When we have a horizontal basin floor, we have an 11-degree slope break. This forces the flow to slow down and all the sediment in an enhanced suspension. On the other hand, if we have a 4-degree basin floor, the slope break is only 7 degrees. So the deceleration is a lot less. But also with a 4-degree basin floor, we still have gravity acting towards our flow while it transverses this basin floor. On the left side here, you can basically see always the main depot center of the deposit. And you see with the run 4 that had a 0-degree basin floor, most of the deposit was was deposited very close to the break of slope. And for run 6, where we had a basin floor of 4 degrees, a lot of the deposit has been transported further out into our basin and actually only been deposited at 3 meters after the base of slope. For the volume concentration, we always had, so when we changed the volume concentration, we always had quite elongated runs. What changed was basically the length overall, but also the cross-section of these deposits. You can see in run 5, we have, first of all, we have a very kind of flat deposit that thickens very much to the end. Whereas in run 8, we have more of a wedge-shaped deposit. And run 8 is as an example for lower volume concentration. Another difference is that for the runs with higher concentration, we get an indent into our deposits. And this tells us that there was a lot of bypass happening when the flow left the channel levee and started to actually deposit on the lobes. There was still a lot of bypass happening in the proximal area, whereas we don't really see this indents in the lower concentrated flows. And overall, you can see, of course, that higher concentrated flows have a little bit higher of starting velocity, and also the velocity loss doesn't happen quite as fast as with the lower concentrated flows. And one of the reasons we see this is the effect of hindered settling. So with hindered settling, basically, the more grains you have in your flow, and they can interact with each other, then the settling of individual grains get delayed. And this happens at least at a concentration of 10%, but maybe even at lower concentrations. And you see all our flows had an input concentration of a lot higher than 10%. And finally, discharge didn't actually change the dimensions of the lobe deposits that were created, but what they changed is where the deposition of these deposits started. So only when we actually turned up our discharge to the highest discharge that we used, we had a proper disconnection of our lobe deposit from our channel. And we created an area of very low deposition that was only filled with the tail of the flow. And this kind of corresponds to something that we would call a channel lobe transition zone. So something that's neither a channel nor a lobe. And a lot of time it's quite erosional, or there is a lot of bypass, which would also be indicated with just this very low amount of deposit. So interestingly, when we now look at the UVP data, there is not a lot of change in the overall velocity. So the main changes are actually in things like amount of deceleration at the slope, effects of hindered settling, and momentum in the flows that steer the different dimensions of our lobe deposits. Another thing that came out of these experiments was something that's most of the time is not really discussed when we look at our deep water deposits, because most of people talk about deep water deposits and what they mean are basically the sandy part of the deep water deposit. But what we could see in run 8, at some point, all our sand was already deposited, but still our flows was going with almost 25 centimeters per second, traveling further on and still depositing all the silt material that we had put into our flow. And this is not actually that surprising, because in this 3D flume, what always happens with the silt material that we put in is that the silt material would have traveled way further than actually the dimensions of our flow, and they in turn get reflected. So they cannot quite travel freely. But you can do a very quick calculation on how long the flume would have to be for them to freely be settling out of the flume. So you would have to have at least 20 meters of length for them to settle and not be reflected at the frontal flume walls. But what does it actually mean now for a natural deposits with this kind of silt run out? It basically means that if we just look at our sandy and heterolithic parts of these deposits, we only capture a quite small part of the overall deposit. And this has already been pointed out in some outcrop studies as well. There's this study of Kevin Boulestykes and others that have tried to follow the more silt-prone parts of Lobe deposits in the field. And they couldn't quite follow them until they actually pinched out, but they could already say that there was at least another 18 kilometers that has to be added to the before thought pinch out of the overall Lobe deposits in a system that he's researched in South Africa. And what does this mean in more general terms? So there were always kind of these two schools that wanted to account for the silt-prone successions in this submarine fence. One said silt-prone successions form when we actually do have a very low sediment supply, so it would be steered by allogenic sediment supply. And the other school always said, okay, wait, let's see this kind of silty intervals. They're actually belonging to the lobes, and we just see some lateral part of them, but if we would be able to walk them out, we would come into a more sandy part. And our experiments actually suggest in the second school is right. We can make, of course, a lot more sophisticated experiments than these single run ones. And if we want to see, for example, how cycles of sediment supply influence our deposits, then we have to run subsequent flows. And this is what we did in this study. We run 5 subsequent flows, and we only increased the discharge. So we didn't change any other parameters. It was always the same sediment volume concentration. The topography of the basin didn't change. But we changed the discharge. And what happened when we changed the discharge? So you now see here the series of the DEMs that were created from the laser scans. This is our basin before we have the first run. So we have the first run come in, building this elongated deposit, so similar to the experiments that I have conducted just by myself and not together with Ross. And then you see that after the first deposit, you have one deposit coming in and going just a little bit further out, but already been steered by the existing topography of the deposit that has come before. And then again, it gets more bifurcated, changing its overall descent a little bit, valsing to the sides and creating kind of this composite body. And how does this composite body look like? Here are some cross sections of this body. So this is through the channel. And first of all, we're just building up our preformed levee. And we have some erosion in the channel, and then there's deposition starting. And with the last flow, actually, we filled our channel. So this is kind of what we assume happens when we speak about channels being backfilled. So they've been backfilled because there is no accommodation available kind of in the lobe area. Very close to the base of slope, we get this picture here. If we now do a cut through the lobes. So basically a very aggradational pattern It's just kind of stacking one lobe deposit on top of each other. Just there's a little bit a lateral shift. And only when we go to the very distal area, we see this really nice compensation of stacking. That's always be assumed to be very characteristic for these kinds of deposits. This was very enlightening because we weren't aware that there might be this difference of stacking patterns if you're looking at the very proximal area or very distal area, and that you could basically have a system that shows both, although it's the same kind of tectonic setting, if you will. And here you do on the right side, you can see like a longitudinal cross section that also shows you, first of all, our first deposit sets everything up. Then we have a little bit of progradation before everything just backsteps. And what's also quite interesting in this set of experiments was that the channel and levee are more influenced by the sediment supply cycle that we simulated than the lobes themselves. So you can see here for the deposit volume that is accounted for the slope, we do have just a little in the beginning, and then when we start to have the retrogradation that's connected to the waning sediment supply, we get a lot more sediment deposition on the slope, whereas the basin floor deposition stays more or less the same, only decreases just a little bit to the end. And you can see that in the channel itself, if you want to take it apart a little bit, the channel and the levee, first of all, if you start to increase your discharge, you get more erosion in the channel, and then waning discharge, less erosion. While on the levee in the beginning, you first deposit a lot, and then the levees basically get too high for the flow that travels through them, and less sediment is deposited on the levees. So in a nutshell, basically, this means that the channel levee parts of the systems are more influenced by the sediment supply cycle than the lobes are. Coming now to just my example 3, and this is basically something that's really in progress, but I think it's quite exciting, so I wanted to share it with you. And this is something I'm started looking at and will be looking at in the future more as well. And this is about the transport and the deposition of black carbon. What is black carbon? So everything from charred wood, charcoal to soot is counted as black carbon. And that's basically all partially combusted material. And we can create these kind of materials during wildfires, but they're also, of course, created by our burning of fossil fuels. So in some cities with very bad air quality, you get these soot deposits that have basically been, from the air onto the ground. So it's not just kind of a question about what happens with natural produced black carbon, but it's also interesting for anthropogenically created carbon. And for these kind of preliminary tests of what you could do, I have used one of the 2D flumes. As actually, I've been out to do this experiment just at the end of October, so I haven't even drawn up my own sketch of it yet. So I'm using a sketch of Mac Baker here, but everything, this whole setup is basically the same. The only difference is that I used a false floor that's basically spanning from the inlet box up to 4.5 meters into this tank that is 5 meters long altogether. So the current doesn't reflect back from the wall, but travels underneath when it reaches the end of the false floor. I also use this flow tracking video camera, and I used some UVP probes as well. which meant that I had to do every experiment 2 times because you cannot use the camera and the UVP at the same time. This is just due to the setup at the University of Bangor. So this is a picture of the 2D tank. Yeah. And here I took a picture of how it looks up before you actually lift the lock gate. So on this side, we have the not yet used part of the flume tank, while we already have added sand here and the black carbon and also the water that we need for our flow. It hasn't been mixed yet because when you mix it, you have to instantaneously lift the gate so the flow can start traveling across it. So I just want to show you a couple of videos. So this video, okay, it says sound. So in this video, what you could see was a flow that had mostly sand as a composition, but 5% of charcoal mixed into it with quite big charcoal grains. These charcoal grains were 2 millimeters to 6.3 millimeters thick. And some of you might have seen them saltate across the bed, but others of them have been transported further up in the flow and have been moved by these eddies that are created. How does this look like if we actually use the same amount of black carbon concentration, but with grains that are finer, with grains that are actually smaller than 1 millimeter? And that's what we are going to see now. If the video works. So one of the things that probably strikes you first is that with our smaller grain size, it seems that the sand content and the black carbon content is mixed a lot better. And that what creates the blackish color of this. And this is, on some level, this is true because the bigger our grains are, the harder it is for them to actually be incorporated into the flume due to the hydrophobic character of charcoals. So after the runs, I've drained the flume tank and I've taken some samples at different distances after the lock gate. So at 0.5 meter, 1.5 meter, 2.5 and 3.5 meters. And these are just some examples for these samples. This would be a sample of the very coarse grain charcoal, and this is an example of the finer grain charcoal. And basically what I want to do now with the samples is to evaluate them more quantitatively, so really use geochemistry to see what is our concentration of charcoal in the different samples. And I also want to use my UVP data to see if the black carbon concentration has an impact of the flow regime. Though for this, and I didn't show you any videos of that, I've basically increased the concentration of the black carbon in the flow to have it up to 45% of our sediment mixture was black carbon materials that we used. And to just kind of finish this talk, and I hope you had a little bit of insight what can be done with analog modeling in deep water systems. I just want to give you an outlook what will be the future of these flume tank experiments. And some of these have already started some of these themes, because there are some people working on microplastic and pollutant transport occurring in the deep sea. There's definitely a theme to work a bit more on turbidity current and contour current interaction. And there's a team of researchers from the University of Bremen in cooperation with the University of Utrecht that have already done some preliminary experiments, and they want to build further on that. There's definitely the big question of what of our what of the product that we see is actually steered by allogenic signals versus autogenic signals. And the second example that I showed you is one experimental series that definitely plays in there, but it's very kind of limited just to the discharge. And of course, there are much more parameters that are important for that, and they still need to be tested. And there's definitely now a growing body of work that focuses on the interplay of sediments and life interactions. So if we do have bacteria in our flows, what would be the difference? Or if we had already a substrate and we have a flow running over the substrate, and the substrate is unenriched in bacteria, does it make a difference? Does it not make no difference? And so on. So with this, just giving my acknowledgement to the IAS who funded my latest work, and all the people in Utrecht, and those people have collaborated from the University of Manchester. And I hope you enjoyed this talk and have some questions.